2, clear takeoff, left hand. Takeoff left, it is 1. Left land, swim west, copy. Crossing 2-1. Crossing at 2-4 is
Hello and welcome to the Blueskies Podcast. I'm PR Ganapati, your host.
Just 70, Roger, report type southeast, connection, 4, the midway, and view still like this.
We're continuing our conversation with Commodore Jaideep Maolankar, and today we're going to spend all our time really discussing the light combat aircraft, both the Tejas as well as the Navy LCA. So welcome back to the program, sir.
Thank you.
So, sir, you had mentioned your initial contact with the LCA was when that fat dossier landed on your table in the ship, over 700 pages of the design document for the Navy LCA. But how did you re-engage with the program, and how did that journey begin with the LCA testing?
So around 2005, I had pretty much finished with my mandatory QRs as a commander in the Navy. I had done my flight commander's tenure, followed by a squadron command, and then I had moved on and done a frigate. I had commanded a frigate for also a year. So that's about the time when they start pulling you out for giving back to the Navy and make you do staff jobs. So all the fun jobs are over, and now the hard work starts. So I was pretty terrified about that. And I'd kind of kept track of where the LCA was going, and what a little bit of news used to come out occasionally once in a while. But it was pretty much a deathly fear of being stuck behind a desk. So, which is when this thing came about. That's about the time when NFTC was also being asked to start providing inputs and feedback for the LCA Navy program. So they figured
and the NFTC, for the audience who don't know, is the National Flight Test Center, right?
Yeah. So they figured that it's the right time to induct a Navy pilot. So they kind of I'm not sure whether it originated from NFTC or it originated from Naval Headquarters, but whatever. Between the two of them, they got together and decided that they would. So I was again, as usual, asked to volunteer for which I pretended to do it very reluctantly, but I was completely thrilled. Absolutely thrilled to have that opportunity. I'm not sure I really knew what NFTC was all about or what I was getting into. Frankly, I had no clue how much fun or how interesting the program is going to be. It was just a very selfish reason of avoiding staff work. And frankly, this is the only way in which I could continue flying, because beyond squadron command, there really is. You can only do some token, nominal kind of flying. So this sounded very interesting for that reason.
And which year was that, and what stage was the
So this is
LCA
2005. I joined in August 2005, and at that stage the LCA Navy was still far away. It was still far away. It had not even been rolled out, for that matter, and the LCA program itself was in its infancy. I think when I joined, they had done about, if I'm not wrong, close to 200 odd sorties. I mean, we were pretty early in the program. We were flying TD1, TD2, and PV1 was the new aircraft, in the sense that it would, you had to be briefed specifically about its differences and things like that. But primarily it was TD1, TD2. That's the stage where envelope was we had gone supersonic, but envelope was pretty restricted still. G was restricted. Controls were fairly basic. Um, I mean, you couldn't even do loops, as I discovered to my horror. That
Okay. And just for the audience who are not familiar with these terms, what is TD1, what is PV1, and what is the envelope when they talk about an aircraft's envelope?
So the LCA program actually is a composite of what you see. The LCA that you see in the squadron is actually a already iterated and modified version of what was the original first aircraft that flew, which was Technology Demonstrator 1. So actually, the program was initially run as a technology demonstration program called FSCD Phase 1, Full Scale Engineering Development Phase 1, which was supposed to be two aircraft, and they added a third aircraft in that called PV1 within those same funds. These aircraft were with the old standard G404 engine, that's the hydromechanical fuel controls. It had rudimentary kind of electronic controls only for the reheat portion, not for the basic engine was still hydromechanical controls, which means a mechanical linkage from the throttle to the in the cockpit to the FCU, etc. The cockpit was of the older standard in the sense we had two MFDs, we had the older standard mission computer, the older standard HUD, a few, I would say, odd looking standby instruments. And it was primarily intended to prove out the basic technologies.
Aha, okay.
The other major differences on those aircraft were that they had a wing originally designed for the R60 missile. So this aircraft was designed something along the lines of the MiG-21 Type 77, wherein the two air-to-air missiles was considered to be the standard fit. So everything of the aircraft was to be done with those two missiles, to the extent that you could not even fly without the two launches. I mean, that's the net result. So you can't really have a absolutely clean LCA. The advantage, of course, is that whatever figures get quoted, whatever demonstrations are done to you, they are in a more realistic, usable config. So the wing was the older standard wing. Like I said, the engine was the older standard engine. And I would think even the fuselage was much more metal. The wings were pretty much the same, barring the fact that they were not strengthened for the R-73. So it was, and of course, many other details in the subsystems. It didn't have the pre-cooler for the, the environment control system. That is an additional cooler for the air just as it comes out of the engine. It didn't have that. So in that sense, it was substantially a different aircraft, and these were to be used for the initial validation of these new technologies. These four major technologies, which are the supposed to be the pillars defining the LCA program. That is carbon fiber composite primary structures, digital fly-by-wire, glass cockpit, and what was the fourth? Multiprocessor controlled. This is a very archaic language. Multiprocessor controlled systems. That is software controlled. Even utility systems being of that. So these were kind of the basic kind of definition of a fourth gen aircraft, and that's what these aircraft are supposed to do. PV1. So that's the first two aircraft, Technology Demonstrator 1 and Technology Demonstrator 2. And then there was PV1, which is Prototype Vehicle 1, which was originally intended to house the Kaveri engine. So it had a bigger intake and things like that, a little bit of different boat tail, I think, which since that did not fructify in time, so it was backward modified again to fit the G404 engine. And since it had bigger intakes, so they kind of fitted a spill door to spill the excess air, but it still retained several limitations, additional limitations originating from this reverse modification to make it backward compatible again to the 404. So that's what the 3 aircraft which were in the program at that stage.
So this is before the the limited series production. This is before that then.
This is well before the limited series production. So because after that we had another tranche of what we call PVs, that is PV2 and PV3. PV5, that's the trainer, that's a separate line. But in the Tejas stable, there was one more layer in the middle, which was PV2 and PV3, which were trying to get them up to an operational standard. That is a strengthened wing, because the Air Force had decided to change the primary armament to R-73. And of course, fitting some sensors. The avionics was upgraded to a open architecture mission computer, three MFDs, 0 electromechanical instruments in the cockpit. So even the backup instrumentation had changed. Pretty much the cockpit that you see now, that cockpit standard, or rather that avionics standard, the cockpit still underwent many iterations, but that avionics standard was pretty much the what came in with PV2 and PV3. And then the next gen was the LSPs. Now this has been one of the things of the LCA program, that we have had to introduce all the constituents of the final aircraft. That's all the sensors, the helmet, the radar, the EW, the pods, the weapons, all the external stores for that matter. They have all been introduced progressively. So although I think the LSPs were originally intended, they were termed LSPs because they were originally intended that they could actually be de-instrumented and used as in-service aircraft. But as it turned out, they are all prototypes in all but name, because each one had some incremental standard.
Okay.
The other big thing was that because we did not do full envelope on the TDs or the PVs, therefore many changes came in late in the program, and therefore the LSPs also incorporated several structural mechanical kind of changes also. That was also something which was progressively built up over the LSPs. So although they were termed LSPs, I think the only real change was that they were built by aircraft division rather than the ARDC. Even within HAL, they have these divisions which are almost like corporate behemoths. Each division itself is pretty large, but the prototypes are supposed to be built by ARDC. They're a little more hand built, not using the production jigs and things like that. But the LSPs were built in a facility which was more akin to the production standard. That was about the only real change. Apart from the fact, of course, that each LSP literally had some major incremental update, like a radar or the helmet, or strengthened stations for some of the stores, as it became evident that this particular store is going to need some strengthening. So that kind of mod. So every LSP is pretty much unique. I would think that for any specific capability, there would be typically not more than 2 aircraft of the right standard. I'm talking about within the LSP thing. This is, of course, what is needed to get everything together, because the final production aircraft has to have everything, because the an in-service squadron needs all its aircraft to be of a identical standard, at least similar, if not identical, but at least similar. So maybe it was this naivete of fleshing out or scoping out a program with just 2 and 3 prototypes. Whereas, although it constitutes an overrun, actually, if you look at it in the big picture, it's pretty much par for the course. The overall number of aircraft that have been used is pretty much par for the course. It's not really any different from anywhere else in the world. It's just that because we artificially, I think, we are pretty arrogant. As technically we are pretty arrogant. We really think that we are so much smarter than the rest of the world. But it's pretty much we've done pretty much the global standard.
And so initially you were involved with the envelope expansion for the Tejas, isn't it? What are some of the things that you did there?
So, I mean, the aircraft for its operationalization needed, first of all, its basics needed to be done. That means its envelope needed to be finished. And I'm talking about the, the high-speed end of the envelope, the supersonic portion, the high alpha portion, the high G portion. So these were the primary elements of the envelope. There are, of course, other aspects of the envelope also in terms of whether you look at it in terms of environment, that is flying through rain, landing on wet runways. There are crosswind. There are many such the engine distortion envelope. That means its tolerance of adverse flight conditions, etc. So there are many elements which many aspects of the combinations of parameters that an aircraft can face, which need to be tested out. I mean, a test pilot should always see any combination first, any combination that is possible. A test pilot should see it first before a squadron pilot, ends up seeing it. So that is what we call as opening up the envelope or expansion of the envelope, whatever terminology you use.
Right. And so, you've done some interesting work on the high AOA or high angle of attack, high alpha regime, and as well as, on the, flutter and the speed portion, particularly this negative SEP at low altitude. So it sounds like a very scary thing. So I'd love, for you to just explain this in layman terms. What did high alpha testing involve? How do you go about it? And
so chronologically, it was speed first, and then we did speed first, then we did alpha, then we did G. So that's how it kind of panned out. So Flutter. So I think maybe we'll do it in that order also. That
sure. Yeah.
Probably. Actually, the Flutter story for me really starts from LUSH, which is the limited upgrade of the Sea Harrier. And what happened was, as I joined NFTC, is also when the Navy wanted to do LUSH. So the first 2 odd years, I was doing half and half. So I am not sure I did very much. I mean, I flew the LCA, but I didn't really take primary responsibility for any of the major tasks because I was in and out of Goa most of the time doing LUSH. So LUSH was it's a bit of a digression, but it kind of builds into the LCA envelope. So if it's okay, I'll talk about that bit.
Definitely, yes.
So LUSH was a complete program in terms of sensor upgrade, addition of a radar, a data link, new displays, and a new missile on the Harrier. So and the integration was done primarily by IAI. The flight test was responsibility of IAI with only the ground servicing crew, the aircraft of course, the ground servicing crew and the flight crew to be provided by the Navy. So that program I kind of did with all the FTs were IAI. The telemetry was manned by IAI. The flight test planning was done between them and me. I mean, flight test team was grand total of me at that stage. So even though it was a 2 aircraft program and it was a data link program, so I had really struggled to explain to people that I can't fly, 2 aircraft
Two aircraft at the same
simultaneously.
time.
And unless I fly two
Right.
aircraft simultaneously, you can't prove out the data link. But the aeromechanical part of that was interesting because we were doing it without participation of the OEM. So it was a full regression program. That means you take the existing aircraft and understand it completely, and then add on these new stores, that is the new missile, Derby missile, and the new radar with a new radome. Add on these two, and then see what the changes you made, with the hope of retaining the original flight envelope capability of the aircraft. So it was they laser scanned the aircraft. They recreated the aerodynamics through CFD. CFD is probably good enough for evaluating changes. So there was basically two things. One was the fact that we used CFD, which is reasonably okay for evaluating changes. And the second major thing that somehow I had the wisdom to insist was that we would not change the stability of the aircraft in terms of center of gravity. So the new missiles were all made to match the original, the Magic missile, for example. So we made sure that we matched that. So we didn't disturb that, because the Harrier is particularly sensitive to CG variations because
Right.
of the hovering, etc.
Hovering, right.
And the second major thing that was an act of great wisdom, frankly, at the end of it, was not to change the shape of the radome. So it was tempting to go the way of the FA2, which is a more bulbous radome, so that you could house a bigger antenna, more power, better radar performance, etc. But that had caused a lot of trouble with engine surge margins on the FA2 program also. So I didn't want the Navy to get into that part of the envelope at all, or working around engine, because that was clearly even beyond IAI's
Right.
capabilities or their skill set. So we said let's avoid that. So we stuck to these two things, and that really helped to make the program really clean, and it just went through beautifully. It was a very nice integration. So one of the major things that we introduced in that program was the use of air-to-air refueling for speeding up the Flutter program significantly. Now, I mean, it's used the world over, but in India we've never used air-to-air refueling as a support facility, infrastructure or facility for flight test, in order to speed up flight test. So they insisted that no, why don't you, since the Harrier is capable of air-to-air refueling, the Flutter program will just go on forever if you don't use air-to-air refueling. And we just followed them. When I asked, and I was very surprised to find that I was given as much air-to-air refueling as I asked for. So that was one.
And these were Air Force assets, because
These
the
are
Navy
Air
didn't
Force
have.
assets, obviously. It was an
Okay.
IL-70. It used to come down. In fact, we brought the Harrier from Goa down to Bangalore, because it was in the monsoons. So Goa monsoons is not something worth trying to do flight testing in. So we brought it down to Bangalore, and the tanker would come down, and Bangalore LFA. I had the pleasure of flying 4.5 hour, 5 hour sorties, 7, 8 refuelings each time, because all you're doing was plug in, quickly get to the height and speed combination that you want, and go right back and plug in, or rather you wait till the Flutter analysis is done by the telemetry crew, and when they tell you it's good to go, then you plug in again, you quickly fuel up and go right again. So when you realize that the fuel quantity on the aircraft also makes a significant difference to the Flutter
Of course,
characteristics.
right.
So you need to be as close to full as possible, because those are normally typically the more problematic configs, the heavier ones with more fuel in them, more inertias, that is. So I even ended up taking the tanker up really nice and high. I mean, even tanking is normally done preferably in a fairly restricted kind of envelope, speed as well as altitude. You don't really like to go too low or too high. But because we wanted to get to those heights and speed with as much fuel as possible, so we needed to unplug from the tanker as close to that as possible. So we couldn't really do too much with the speed, but I could take the tanker up, and then you start hitting. You're actually sometimes literally falling off the tanker, because as you fill up, you need more and more power to keep up with the tanker, and you're pushing that drogue. Also, you're carrying the drag of that drogue on the aircraft which is receiving the fuel. So you find that when it gets too much, you're at full throttle, and the aircraft just gradually just falls off the tanker and unplugs. So that becomes the natural kind of limit. So, but with all of this, what ended up happening was that I actually ended up having to study Flutter very deeply, because you were doing it literally in real time. Each incremental step was in real time. You were literally every 10 minutes you were doing a next speed and height combination.
Just need 70, Roger, report time southeast, connect for 728 and you selected.
Right. So I'm still struggling to get my heads around what Flutter is. A few other people have tried to explain it, but I'd love to hear your explanation, especially for the layperson.
So Flutter is, if you just think of it, you hold a sheet of paper from one end and just put on the fan, and you find that the sheet of paper starts fluttering. Literally fluttering, right? So that pretty much is something which any aerodynamic structure will do, or will have a tendency to do, unless there is a proper design which makes it resistant to it. Now, why does the paper do it with just a gentle breeze coming out of a fan? Because it's got extreme flexibility in it. So clearly, the elasticity, the resistance of that structure to being deformed is clearly one of the forces. The aerodynamic forces are clearly where the energy is being drawn from. There has to be a transfer of energy from the original source into this fluttering movement. That is the energy transfer is the real problem, and that's the mechanism which needs to be studied. So it's a balance of the inertial forces, that is the masses, the way these masses are pivoted and the way they flex in terms of let's say a swept wing design, or a delta wing design, or a straight wing design. You can imagine that even if the wing is the same, but if I just keep changing the sweep angle, it will tend to move differently when I look at it as an elastic structure, because its CG has shifted aft of the point where I'm holding it, the point about which it would tend to pivot. So it's a combination of these inertial forces, the aerodynamics of that structure. How does the lift change when it moves under load? How does the lift change? Does it increase? Does it remain the same? The combination of these two, it's very simple to visualize when you think of these simple things of a paper fluttering. It's a lot more complex when you actually try and do it analytically. And in fact, that is probably the defining aspect of the hazard out of Flutter. Unlike many of the other aeronautical science disciplines, this is one of the most inexact sciences. I would say lifing and Flutter are the two inexact sciences in aeronautics. Everything else is amenable to good, strong analysis. You throw a lot more computing at it, you throw a lot of brain power at it, and you can be pretty good at predicting what is going to happen, which means you can design and be sure that it's going to behave as you expected, and therefore even testing it becomes relatively easy. You just need to, in quick jumps, you can cover the full envelope that is intended, because you don't
more
really.
validating, what
It's
has
just
been
validating the
computed.
thing. Flutter is not like that. Although all the scientists who work on aeroelasticity will be very upset when they hear me say this. But I mean, I say this all the time, so it's not something new. And this is pretty much the way it is.
And do you experience Flutter as a pilot, or is it just picked up by the sensors?
No,
And
I mean,
what's the danger when it's uncontrolled?
if flutter occurs, you're probably going to break up the aircraft. It's that way.
Wow.
So the thing is that when the structure starts flapping, now if it is an extremely flexible structure like a piece of paper, it's okay. But typical aircraft structures will not tolerate that kind of movement, and they will literally break the aircraft apart, because the structure cannot be designed for taking that kind of motion and loads. So the problem with flutter is that it sets in quite often explosively. Very, very suddenly it will set in. That means the structure is damped. Any disturbance. The thing is that any disturbance, any turbulence in the air can also set off an oscillation in the aerodynamic surfaces, which, if this combination of all these flutter forces is not favorable, will tend to aggravate this motion, and then it builds up, and it will just snap off these surfaces. So this set in fairly rapidly. It's very hard to, just simply by looking at the behavior of the aircraft, it's very hard to tell whether you are getting close to a limit or not. The only way you can do it is if you can see how disturbances are being damped out. Disturbances tend to get damped out when the structure is when the whole system is stable. If you have flutter modes which are gradual in their onset, then you will see a gradual decay in the damping, and when the damping drops too low is when you will have flutter. This is one of the assumptions on which a lot of flutter work is based. However, there can be anomalies in the structural behavior or even in the aerodynamic behavior. You can have onset of vortices, you can have onsets of separations which have not been predicted in the analysis, and therefore your analysis is not showing these sudden changes in the behavior. And you can even have fairly explosive onset of flutter, and paradoxically you can even have scenarios where you find that the damping is increasing and then suddenly falls off. So the point being that with flutter you are really feeling your way towards opening the envelope, and the way I finally rationalized it in my own head was, any deviation from the expectation is a cause for concern. It's not just a drop in the damping when the damping gets too low, which is a cause of concern, but even an unexplained increase in damping can be a cause of concern, because that can be a warning that things are not as you think they are, or as you expect them to be, and therefore be cautious.
Mm-hmm. And you're instrumented to measure this damping, or is that being telemetered and then communicated?
So there are various methods of doing it. The most typical method nowadays with fly-by-wire aircraft, etc., is you inject disturbances through the control surfaces. That means you have these automated routines in the software which you inject them, and it, over and above what is being demanded by the pilot or by the normal fly-by-wire software, over and above that you introduce a little frequency sweep on the control surfaces. High frequency, I mean, you're talking about few hertz going up to few tens of hertz. At that rate you move the aerodynamic control surfaces, so that introduces disturbance into the thing, and then you stop it, and then you see how does the disturbance decay, how does the structure damp out those disturbances. That's one way of doing it. Another way of doing it is you use the disturbances that occur from the natural, air turbulence. Uh, you inject this, or you take it into an area where there is some amount of turbulence, so that there is some upsetting, and then you are basically you basically have these vibration sensors at all over the aircraft, and you are tracking how are those sensors, the traces coming out of those sensors. So it's a little difficult to explain Flutter without moving my hands around and being able to draw on a whiteboard. But yeah, this is pretty much it. Now, you need to obviously do a Fourier analysis of the vibration sensors, look at frequency modes, each mode. I mean, if you have seen, there used to be this toy which a lot of these hawkers would sell. It's a bird with two wings. It's got a wooden body and two wings which are hinged, and it is suspended through strings with from the wings. And when you move it, the whole body of the bird goes up and down, and the wings kind of flap. So that is the way you can visualize some of these motions. So every aircraft has multiple modes in which it naturally wants to flap. So one of those modes is something like what that bird would do. That is actually close to the second wing bending mode, wherein you're looking at as if you hold an aircraft up by two fingers, one under each wing, and you just push down on the body and leave it. The body would bounce up and down, and the wings would flex around with these two nodes, fulcrums, where you're holding it up. The first bending mode would be just the wing by itself. If you just hold the body of the aircraft and just tap on the wing, and how would the wing flap and sort itself out. So like that, there is basically any major aeroelastic element of the aircraft. You took the fuselage or a wing or a tail fin, etc. Each one of these things has an unique behavior or a unique influence, which the composite of all of this is what makes the aircraft behave the way it does. So you can have one particular flutter mode by itself getting into trouble. You can have two different modes, that means two different types of motion tending to synchronize and thereby suddenly adding energy. That's where the explosive element comes in. They are, as long as they are at different frequencies, they are by themselves individually, they are all damped. But because their frequencies are slowly changing, when the frequencies coincide, you can have a sudden explosive change in the damping, and each mode is adding or aggravating the other. You could have some mode serving as an energy transfer mechanism between one mode and the other. I mean, it's a black art. Let me put it that way. There is of course sufficient scientific rigor in it, but it's not sufficient to guarantee that the aircraft is going to behave the way you expect it to behave. Which basically, for flight test, amounts to what? It means you have to flight test. You cannot release to service anything that you have not physically tested. You can't release an envelope to service by analysis. So if the aircraft has been designed for a speed envelope which is say 1000 knots or something like that, indicated airspeed. Now, even if that aircraft cannot, suppose that aircraft cannot achieve 1000 knots, even if you take her to a ceiling and put her into a vertical dive, and even if the terminal velocity is not 1000 knots, then you can't write 1000 knots in the manual, even though you are completely convinced that the aircraft is capable of flutter-free flight up to 1000 knots. You can only write what you have actually taken it up to. So if you've taken it up to 900, then 900. That's the speed envelope of the aircraft. It's fine because you can't really exceed it. Although someday somebody will find a way of doing that. But one, you have to flight test. Second is, when you are doing flight tests, you can expect to see variations, surprises as compared to what was expected. So this is one element of flight testing where skill is not is something that can keep you safe, because there is no skill in which or skill set you can acquire, or which you can prepare yourself to say, I will fly her out of that Flutter envelope.
Right.
The skill or the knowledge is in in a very controlled, calibrated manner, putting the aircraft into those intended test conditions without infringing something else, and thereafter being able to read the results, being able to understand the signs, the results that you see. They are signs. They are telling you something which you need to understand. If you can understand that, you are in business. We have taken some things down to very low figures of damping, because we realize it's not the absolute damping magnitude of the damping that is important. It is the trend in the damping. You can have damping down to very, very low values, and all that will happen is you will get a little oscillatory kind of behavior on the aircraft, but nothing else. It's not unsafe at all. It's just a little weaving kind of motions you might encounter, or not at all. You may not even feel it, but there's no danger. Whereas you may see damping rising very rapidly, and actually that is telling you that if you push any harder, it's just going to explode on you. Literally, it's called explosive flutter. So that is the whole thing about Flutter. Now, flight testing it, therefore, like I said, is you have to put her in those test conditions in a very controlled, calibrated manner, which is pretty easy. It's trivial. It's a trivial activity when you are talking about speeds and heights which are within the level flight capability of the aircraft. You just take the aircraft to that height and speed, and accelerate to that speed and throttle back and hold her there. There's nothing to it. And then they run this software routine which moves the surfaces, and you feel a little bit of a vibration on the aircraft, but you don't really see anything. And then they get the data, they look at it, and they tell you it's okay to go to the next one or not. It's pretty boring, actually. It's very anticlimactic kind of testing. It's boring work. The thing changes completely when you now get to parts of the envelope where the aircraft cannot reach with its own thrust. So let's say the aircraft is capable of 600 knots at in level flight. She's capable of accelerating to the thrust is sufficient to take the aircraft up to 600 knots. But I want a speed envelope of 700 knots. Now, how do I take the aircraft to 700 knots? The only way is to put her into a dive. You can ask a question, why do I want to take her to 700 knots? Because if an aircraft can achieve 600 knots, let's say at sea level in level flight, if I dive her from 10,000 feet, she will have reached 700 knots by the time I reach sea level. So, the frontline pilots are going to take the aircraft to those kind of speeds. Now, how do you test it? It's not just a matter of putting her into a dive. There was this old poem, of put her into a dive and see if she holds whole, and if she doesn't, then I find myself in a ditch, and an old test pilot ditty like that. But that is no longer acceptable. I mean, in the 50s and 60s, the bulk of the test pilot, that mystique and the whole business of being a daredevil, etc., originated from this thing of the death dive, that you would just take the aircraft up to a height and put the nose down and see if she comes out intact at the end of it. But that is obviously not an acceptable method in this day and age. So you need to attack it, slice by slice. It's not one big mega put her into a dive, you're offered a bonus by the company, and if you're alive to collect it, good for you. It's not that way any longer. So you have to figure out a way in which you are able to, in a calibrated and assured manner, get to a certain heights and speed combinations, while you have to be in a dive to do that. So it's basically a series of very incrementally steepening, increasing dives, which needs a lot of planning to do in order to get there, because it's not just a matter of oh heck, I exceeded the speed that I intended. I intended to reach 620 knots today, but I ended up at 640. No, that's not the point, because the safety lies in that if I have seen how the aircraft is behaving at 600 knots, then I look at it and say, okay, I think I am reasonably safe up to 620. By looking at this data, I don't think anything will change dramatically. If I have flown at 600, I think I should be okay up to 620. So the next test has to be at 620, which is within the scope of the coverage provided by the previous test point. If I go to 640, I am out in a unknown zone.
Right,
Because
right. Wow.
to get to 640, to say whether 640 is going to be safe or not, you need the 620 data. So you can't have a pilot saying, okay, let's try 620 and I'm sorry, it went to 640. You can't have that, because then you are subjecting the aircraft to just risk. There is just risk with no risk elevation behavior. So now you're talking about doing this as you are approaching closer and closer to the terminal velocity of the aircraft. So it needs to be done in a very, very calibrated manner. And the flip of, one can say just be safe and do it really slowly. How does it matter? But imagine each one of those supersonic, what we call top right hand corner, that is the high altitude, high Mach, high indicated airspeed combinations. Those, the aircraft can basically reach those points once in a sortie. So each attempt or each failed attempt is one full sortie gone, which can be, all the flying that you do in that one day. So each time that you fail, you are finally going to get frustrated and one day just shove the nose down and add, another 10 degrees extra to the dive and exceed it. Or you're going to consume so much of flying that your management cannot afford it. So it's a contest between flight test efficiency, flight test safety, and this fact that the science itself is a slightly inexact science. You need to figure out a way in which you can, with some degree of precision and some degree of a high degree of control, guarantee that you're going to achieve the test cases that you do. So that's the problem in this negative SEP. Negative SEP portion is where the part of the aircraft, part of the flight envelope, which the aircraft cannot achieve in level flight. It does not have it. It does not have the thrust to be able to fly in those zones. So we ended up spending a fair amount of brain power on trying to figure this out, and a lot of it we've written in that Yamashita Rajkumar's book, the Tejas, the latest book that he's released, Brilliance. It's kind of described in there. So frankly, it might be a better thing if I point people in that book.
Yeah, definitely. I just wanted to understand from the pilot's perspective, what do you experience? What are you trying? And I think we've got a sense of that. You're just feeling your way around very incrementally and slowly to that point.
You have to have the discipline that comes from analysis. On the basis of the performance analysis, you make a performance plan, and then you fly that as accurately as you can, and keeping your all your senses open for looking for any signs that are not being obviously picked up by the sensors, or sensors. All the data is going to be analyzed afterwards. You need to see if anything is going off, anything is going awry while it is happening. So anything you feel uncomfortable with, you have to back out of it, which is basically slow her down. Let's just throttle her back, and maybe on some aircraft it's a good thing to just put a little bit of G onto the aircraft, a steady G. It tends to damp out things. So it's a very disciplined approach to it. Now imagine you're doing this with refueling. That means you're doing the full sweep in one sortie. So between each test point, you're doing one air-to-air refueling, which itself is reasonably stressful, and then you're doing this strategizing about what is the next test point that you want to do. Quite often, the call that you take is that they're not so sure. They're not saying it's unsafe, but they're not so sure how safe the next test point is. So even if you had planned, let's say, a 20 knot jump to the next test point, you make a shorter increment and you say, let's do 10 knots only. Which means that even your original plan that you had, you may have had a plan for, you may have all the parameters written down for the next 20 knot jump, but you need to quickly iterate something, interpolate something in the middle and figure out a new plan for 6-10 knots. But that's the way it needs to be done. So you can imagine that all of this is only possible if there is tremendous synergy between the pilots, the flight test team, that is, the test engineer, the pilot, and the engineers who've done the design and the analysis. There has to be a complete understanding. It's for every hour that you spend airborne, you have to have spent tens of days discussing it, so that you all have a common understanding of how you want to go about doing the thing.
Visual before visualize. Just 70, Roger, report time southeast, connection, for evacuate, and yield selected.
So, sir, we'll move on from there. But before we move on to the next topic that I wanted to talk to you about, which is display flying, I just wanted to quickly speak about the test firing of the Derby missile. I think you were in the chase aircraft, isn't it, a Sukhoi? And can you tell us a little bit about what that experience was like?
No, Derby. I was when we did the first live Derby. I was a safety pilot. I was planning the sortie and kind of monitoring and controlling the sortie. The Derby, I was the most familiar with it because I had done Derby on the Sea Harrier.
On the Sea Harrier.
So I was most familiar with the Derby, its systems, etc. So I had spent a lot of effort in the integration of the Derby onto the LCA also. I mean, it was actually a low-hanging fruit for the LCA program, because Derby we were already familiar with because of LUSH. Derby had been already specified for LCA Navy by the Navy because they wanted to have a slightly lighter BVR as compared to, say, Astra. LCA Navy, bring back loads on the carrier, etc. So they said, why not Derby? So Derby had been specified for LCA Navy, and so ADA was already committed to doing a Derby integration on an LCA, which kind of makes ultimate sense that why not for the Air Force also, and it'll get a quick, really quick and easy within the same original planned cost. You get a BVR capability for the Air Force aircraft also. So that's how Derby on this thing came about. What we needed to do was adapt it properly so that we mounted it correctly. So that was one thing which I spent a lot of effort trying to ensure that we carried it properly on the LCA. The LCA Navy, we could do a better job than the LCA Air Force, frankly. But that's a different story. And a lot of the aeromechanical flying, that's the opening of the envelope, that bit I did. The systems portion, by the time that came around, LCA Navy had picked up a lot of headway, so I did not do very much work on the systems part of the Derby. However, the live firing portion also, since I had done quite a bit I'd done the full separation firings as well as the live firings on the Sea Harrier. So that is another full discipline by itself, weapon testing, and therefore I ended up doing a fair bit of the planning and the execution, of course, for the Derby.
Okay. Mm-hmm. Okay, great. So we'll change gears now to you did a fair amount of display flying on the Tejas at Aero India's in Bahrain. So just tell us about display flying, particularly with an aircraft that is still in development. What is the objective? What are the issues and preparation that goes into it? What was that experience like? What are some lessons we took away from the demonstrations that we did on the Tejas?
So the thought process about display flying is something which it's actually the first exposure that typically a kid has to flying is somebody doing a display, and unfortunately many pilots, the last sortie that they do is also a attempted display. So it is something which is an extremely important element of aviation, which does not normally get the kind of scientific rigor, literature, structured learning, structured discussion that it merits. It is a full discipline and a science by itself. Starting with why are you doing the display? So the bulk of the displays that all of us are exposed to are, in the earlier years, when we were growing up, certainly was these what I call the Diwali Mela display. Every air station will typically have a Diwali Mela, and during that Mela, in order to basically for the families and for the general civil populace, you tended to have one of the squadrons would be told, why don't you do some little bit of displays. And then depending upon the personality of that particular squadron commander or whoever was the display pilot, it would be either very aggressive or it would just be basic speed and noise kind of display, or some highly technical. It depended. It was very dependent on the personality of the individuals involved. What is the kind of aircraft that you had, and pretty hit and miss in terms of for that kind of an audience. As long as there's enough speed and enough noise, it's good enough. The idea is to inspire people to want to become a pilot, although it conveys completely the opposite impression of what you really need as a pilot. You need more discipline and willingness to study as compared to just being dashing and cavalier in your attitude. So that is the typical display which people are exposed to. Now, thanks to Aero India, Indians also have got used to seeing Airshow displays. And there is a full spectrum in terms of displays that are put up in order to convince a customer. That means controlled displays with a very small select audience, intending to impress you with a particular aircraft. The aircraft have already gone through selection and already vetting of the parameters and parameter comparisons, etc. But so you come down, then where does the display fit in all of this? With all of this science and knowledge that is available and all the parameters, why can't you just put them together in a table and side by side compare parameters and be done with it? Now, displays are very powerful in terms of conveying a message, because they are a message which the full script is in the hands of the person who is choreographing that display. There are no interruptions possible. Even in a presentation, somebody can interrupt you and disrupt your the flow of thought of ideas that you want to put across. In a display, that's not so. A display is the ultimate uninterruptible PowerPoint, fully immersive PowerPoint with a phenomenal soundtrack, and even a visceral feeling of, you can feel vibrations in your body if you stand close enough to the aircraft. So it is an extremely powerful tool for conveying a message. So what is the kind of message that you want to convey is very important. Whether it's just a recruiting message, speed and noise, fighter pilots are so dashing as a recruiting message, or are you trying to convince Shah of Iran between F-15 and F-14 fly off? I mean, very few people know that Iran was offered the F-15 and the F-14 both at the same time. Now, normally, just off the bat, if you ask somebody which is a superior aircraft, people would say F-15. But it was the F-14's display which convinced them to buy F-14s at that stage. although the F14 was not superior to the F15, but it had a more convincing message. So that's the full spectrum of things. One would ask that, why does HAL or ADA spend so much effort on LCA displays when you have a captive customer? Even for a captive customer, it is very important to do your displays properly. Why? Even if you have a captive customer, and even if he is fully embedded into your full development process, unfortunately, the human nature is such that the bulk of the time will be spent on the problems in the program. Even if you're doing a review, or if you're discussing all the developmental activities, naturally the activities that are working well, you will skip over or hardly spend any time, because they worked out exactly as you have planned. It is the problem areas that you're going to spend the maximum number of hours discussing. I'm talking about the customer with the design teams. So there is a natural tendency for a customer who is too deeply embedded or too close to the aircraft to see only the watts, because you're so close that you're only seeing the watts. You're not seeing the beauty in the aircraft, because it's not yet come into your hand, so you haven't flown the aircraft, you can't fly it yourself, and all you are discussing for week after week is the watts. It's important even for a captive customer like that, for you to show him in a composite whole that this is what you're getting. Forget those watts, just zoom out and look at the whole aircraft, and suddenly it all comes together. That, this whole thing is worth doing, and therefore now when you go back and focus on the watts, you are not looking at them as a all or nothing, make or break, cure this watt or else I will junk the whole aircraft. You get a much better, well-rounded perspective of the aircraft when you see displays. It kind of just slots in together. Dry numbers, even fancy photographs and all, don't really have as much power as a convincing power as a good display. So there are displays and there are displays. Now, what were we doing on the LCA? So the first display that we did was so soon after first flight that frankly it was a miracle that the aircraft flew in front of the audience, right? So it had a limited envelope, and within that limited envelope, they tried to put her through some maneuvers to basically everybody was pretty much thrilled that the aircraft was flying in the first place. That kind of held us through a little bit till the first few Aero Indias, when it shifted to the first few Aero Indias which LCA participated in. It was good enough. But then you could see that in comparison to the other fighters that were being flown, that you could then begin to see the fact that now this aircraft has not grown or expanded its envelope like it should. So it basically drives you into an area of where you are displaying the capabilities of the aircraft in comparison to other aircraft also displaying their capabilities. It's a capability comparison display. It's a technical display. You can fool the lay public with just generally doing some thrilling maneuvers, or some unique maneuvers that means in a unique location, some unique shape. But you are not going to be able to impress the people in the know because they are looking at it as a comparative performance to the next aircraft. Because the next aircraft after your LCA display is going to be a Rafale, or before it's going to be a Eurofighter or something like that, and they're going to compare and try and figure out where does this aircraft fit. So clearly you need to develop a display routine which shows off the capabilities of the aircraft, which is okay. You do need to make it a little thrilling. You do need to make it a little exciting. But that can't be the main substance of the display. That can be in how it is put together, how it's sequenced, and things like that. It can't be in the main substance, the main maneuvers that you show have to be designed to showcase it. The ultimate way in how not to showcase an aircraft is to crash an aircraft in front of a display crowd. So if you could show the maneuver at 5,000 feet, it will hardly be impressive, and you could show the maneuver too low, and again it will be hardly impressive. So you need to show it in a manner where it's safe enough. So what is safe enough? That you can complete the maneuver if everything goes well. That is safe only as long as nothing goes wrong. Typically, you are displaying an aircraft which is yet under development, which means there are still failures that are likely to happen, which you can't be too sure about, or you can't say for certain will not happen. In fact, what we found was that the most adverse combinations of flight parameters that we were generating in the flight test program was during these free maneuvering routines of the air display. When we were doing test cases for alpha, for example, we were able to generate, let's say, X degrees alpha, and we were not able to generate more than that. But when you do it at the bottom of a barrel roll and you're trying to throw into a turn and trying to throw in a very rapid roll rate, we found that we would achieve X plus 2. So it was important to understand that you can't say that I will have everything under control. At the same time, it was important to use this free-form maneuvering as part of filling out the envelope. One is to stake out and do all the test points at the periphery of the envelope, but in between, which is the combinations. These envelope diagrams are typically single parameter diagrams. Height versus speed or something like that. So combinations, what about side slip, what about angle of attack, what about roll rate, what about pitch rate, what about G, those combinations you can only kind of create when you do a little more free form maneuvering. It's like coloring in, drawing the outline and then coloring in and block filling it with a pencil in the middle. So you need to look at air displays with all of this in mind. So we got away with some of the initial ones by just putting together a routine of some standard maneuvers. Then we found that the roadblock was skill levels. That means how much time are you able to dedicate just to display flying. Typically in a developmental program, you don't get the amount of effort and time to guarantee a good, safe display, because it costs effort to give you that flying just for display practice purposes. As opposed to, let's say, a company with a fully developed aircraft which is now developing a routine just to entice customers, they will be willing to put aside a full month each time with a 25 sortie build-up syllabus. Whereas a agency like ours, which is also trying to concurrently do the real development of the aircraft, may not be able to afford that. So you have to ensure that it does not exceed your skill levels. And by that, what do I mean? I mean, you should not have to play it by ear through the maneuver. So, for example, if you do horizontal maneuvers, it's fine, because even if the maneuver turns out to be different from what was originally planned, it's fine. The trajectory is safe, it's horizontal. If you start going oblique downwards, there is still enough escape route, in the sense the trajectory is not so adversely downwards that you can afford to shallow it out and not hit the ground fairly easily. But to commit yourself to a fully vertically down trajectory, you have to have done enough planning, enough what ifs. You have to have all your go no go parameters clearly mapped out. It requires a fair bit of planning effort to go into it. So you can't commit yourself to steep vertical maneuvers, particularly downward trajectory maneuvers, unless you have you can't do it on the basis of skill. You have to do it on the basis of effort, planning effort. So we found that we were not willing to commit to these deep, steep vertical maneuvers because of the amount of effort that we had put in or were able to spare. And anything more than what we were doing would start becoming a skill-based activity, which is not the way it's supposed to be. Second is some of the limitations of the aircraft or the rough edges, the unfinished work on flight controls was beginning to be apparent. When you're trying to show the rapid roll rate, the way in which the roll rate was being arrested, or even the roll rate itself that we were generating, you could see that the aircraft needed some more work. Just by standing outside as a spectator, you could see that the aircraft needed a little more work. You could see that some of the maneuvers were not tight enough because the G of the envelope of the aircraft was still restricted. So basically, we were running up against the limitations of the envelope of the aircraft. The envelope had yet to be opened to its full envelope. And lastly was the fact that you were not showcasing it in maneuvers which could directly and without measurement, with measurement, it would give direct information to the spectator that whatever you are reading in the press is not necessarily the whole truth. Turn rate is low. You can see the aircraft turning in front of you. You can see how long it takes to turn through 360 degrees. If you just bother to sit with the stopwatch, you can see it in front of you. And then you can see for yourself whether the aircraft is really as bad as it's made out to be in the press. Don't forget, this is the period when all articles about anything to do with aviation in the newspapers used to start with whether it was literally any story about anything. Completely disconnected with LCA would start with, because LCA is delayed and because LCA does not meet the requirements, therefore something else would start. That was the lazy kind of storytelling which was happening in the lay press. It's very important that you don't get this kind of you fight your way out of it, because that is also affecting the kind of talent which your program can attract. So I'm building up this picture of how important are these displays and what it's a full spectrum activity. It's not a like I used to keep fighting inside the system. It's not a bandar match. It can deteriorate down to a bandar match that in the old days a guy would come around on a cycle with two monkeys and with that damru, and they would do some gymnastics in front of you. That's it. It's not that. That is not what an air display thing is all about. It's all about convincing people about whatever message that you want to convey. So when will the LCA get exported? When prospective customers think of you when they are cooking up their RFP. They bother to send out an RFP to India because they have it in their head that India also makes aeroplanes. That is not going to happen till you are regularly seen on the air displays. Your air displays are regularly seen on the Airshow circuit. Your products are regularly seen in the right context. They are seen flying there. So how do the Malaysians or Bahrainis see your aircraft unless they get to see these kind of things? So it's a slow burn. It needs to it's like wetting the ground. You need to pour enough water to make sure that the ground is then fertile, and that is when then your I'm saying this because when we went to Bahrain, a lot of people ask me this question, but why are you wasting your time, because you're never going to be able to sell an aircraft in that air show. So you say, no, this is all part of a complete spectrum of activities that need to be done. How to sell an aircraft, whom to sell an aircraft to, like I said, even your captive customer needs to be sold the aircraft.
Excited and happy.
So you need to put together your display for this purpose. So like I said, in the Aero India routines, we were beginning to run up against skill. We were beginning to run up against maneuvers that we could not do because we did not have enough effort to plan the maneuvers or scientific rigor to plan the maneuvers. We were running up against the envelope limitations of the aircraft. So when this Bahrain thing came around, it was a good excuse to just break out of all this and do a fresh thing.
Just 70, Roger, report time southeast, connection. voor de weten en heel veel activiteit.
Right. What was fascinating is that, your 6G to 8G limit with that software or upgrade came just in time. And
it came because of the Airshow. Not just in time. It came because of the
as
Airshow.
in the pressure was because of the Airshow. Okay.
Exactly. So, when you put it together like this, then you come up with a plan and you realize that, okay, how do I go about pushing it so that even to convince the management, for example, that this effort that I'm asking for is worth it. Now, one of the ways I figured was that if you sold it to them as a way of expanding the envelope, or using it as the thin edge of the wedge to force the issue and finish off the envelope. There were some parts of the envelope which were lying, waiting to be opened up, but we were just never really getting around to it because they were not deemed high priority items at that stage. Flying effort was being expended on other aspects of the envelope, but it was lying there untested, and we have developed a firm belief that all these basic things you must test out as early as possible, because if let's say when you open up the G envelope, if something breaks or something is not deemed strong enough, now undoing that or modifying the aircraft for that is going to take a long time. So these are not things that you should do as the last sortie of the program just before delivery of the aircraft to the customer. Cannot be the the edges envelope test point. It can't be. That is just simply too much risk to take, because anything that turns out to be not as planned, you're looking at a straight delay. There's no chance of making up that time. So you have to do these things, in fact, as early as possible, because every time you actually flight test it is where you will invariably have some surprise. Invariably, without fail. Whether you're a developed country, whether you're a developing country, it doesn't really matter. F-35C had to do arrestments in order to realize that its hook was too short. This is coming from a country which had probably its 100th carrier-borne aircraft. So it's not a criticism. It's just simply a matter of fact. It's in fact one of the philosophical differences between a flight test center and a developmental agency. That we are trained to be professional cynics. Everything looks good, but let's see if it is as good as it's supposed to be, and as early as possible. Making, if necessary, all kinds of deviations and compromises in order to get as quick a look as possible, which is pretty much what, for example, the 8G for Bahrain was. We wanted that 8G. We wanted to push that 8G into the aircraft envelope. So even though those prototypes those LSPs were of a slightly different structural standard as compared to the aircraft that were going to be delivered to the Air Force, the series production aircraft, and therefore we would have had to accept a slightly restricted speed band within which that G was permitted. We accepted it. We took it because it made sense. Let's just do it. And in doing so, even that limitation that person is putting is understanding of what's happening on the aircraft. So let's push it, and we insisted on it. In fact, we rehearsed on a 6G aircraft till just before we flew to Bahrain. We had worked up initially here in Bangalore. Then we did a small, like a training camp, sports training camp at sea level in Jamnagar.
In Jamnagar, right.
Because the performance of the aircraft would improve as we went down from 3,000 feet to sea level. So to adjust to what are the expected conditions in Bahrain. And that is also when this 8G software on the thing actually landed up. I'm talking about the 8G software for the display. 8G by itself, we had flown we had just opened up the envelope, opened up the limiters a little bit on the existing software and flown it here. It means to test the structural aspect of it. But embedded within the flight control that is permitting 8G was arrived just before we ferried out. And so we did a few quick rehearsals, but because we had designed the display in such a way that the 8G was only being used horizontally, so it did not change our display so substantially that we had to redo the rehearsals. And so all the vertical part of it was all within the pre-existing capability of the aircraft. We had structured it that way, you know. Now, what was therefore what was it really that we were trying to show in that display routine was we wanted to address specifically all the criticisms of the LCA that had been spoken about in everybody on Bharat Rakshak and Twitter and everything else. Everybody has an opinion about the LCA, and what were the specific things that everybody was talking about. One of the things was underpowered. Okay.
Right. Mm-hmm.
So we said, okay, let's put it in context. Let's show them what power the LCA has, and that means let's do out and out maneuvers which are completely a function of how much power the aircraft has, and let people see for themselves whether yes, it may not have the same thrust weights and power as a Eurofighter or a Rafale, but does it have enough for you to be in the same ballpark, and therefore tactics and skill come into play? Or are you so simply outclassed that any amount of training and tactics and weapon work is not going to give you a chance? So many of the maneuvers were designed to show that. The second was this expanded maneuver capability of the aircraft. We wanted to put out the expanded maneuver capability. So we said, let's show them sustained turns and instantaneous turns. That means what is the max turn rate that the aircraft can generate, as well as what are the max sustained rates that she can generate. So let's do full 360s, in a oriented also in a manner such that a person can stand with the stopwatch and get a first cut feel for himself whether it is 10 degrees per second or it is 18 degrees per second, or what is it, the capability of the aircraft. So you get a direct first hand feel for many of these parameters, and the confidence that we would be able to impress at the end of it was coming from the fact that we had finally expanded and pushed out the envelope of the aircraft to what it was supposed to be capable of. Then you just need to add a little bit of drama to the whole thing. So, for example, negative G. Now, negative G is an ugly maneuver inside the cockpit itself. If you show it in the classic thing, which is upright and pushing downwards, it doesn't really convey too much of a message. But when you show it in some kind of a weird maneuver like an outside turn, the aircraft visually appears to suggest that it should be turning one way, but actually appears to be moving the other way. It just puts it together. It is a little bit of artistically, packaged to be very, very interesting. It is also interesting that that was the way in which we were finally able to expand the negative G envelope of the aircraft to the negative G limit. We were otherwise not being able to achieve the maximum negative Gs. And here, finally, during the airshow routines, in fact, we were exceeding what we were planning to restrict ourselves to. So you add a few elements of this drama into it, and then once you are ready with all of this, then you need to do a little bit of showmanship, a little bit of professionalism in terms of packaging them so that you're not spending, typically an airshow routine is got to be done in a small box in front of a crowd. Now, these high-speed fighters can't stay permanently inside that box. They need to keep exiting the box and then turn around 180 degrees and come back again through the box and do a maneuver, and then exit the box to the other side, and then again turn around. So if you just look at it, 1/3 of the time that you get only is spent in that box doing the maneuvers of interest, and 1/3 is spent turning around at one end, and 1/3 is spent the last 1/3 is spent turning around at the other end. So 2/3 of your time is spent just in turning around the aircraft, which can get pretty boring. So you need to package them, you need to change the axes in such a way that even your repositioning maneuvers are adding to the aesthetics of the display. You need to change the lines. You can't just work on a linear. You need to work in a V. As you get further from the crowd, you need to go up higher so that with the same posture of the audience, they are able to view the thing. You're setting up. You've got to put it on a stage for them. So that becomes the next layer, and of course, then there is this layer of safety, which actually has to come in right in the beginning, because when you're planning your maneuvers, that you have to be able to handle. I mean, one failure definitely. You definitely have to be able to handle any single failure and guarantee that A, you're not going to hit the crowd, and B, that you can recover the aircraft out of that and abort your display and recover it. But the barest minimum is that you should not, plow into the crowd like has been seen on so many displays. So now that is something which is just pure hard work, figuring out what all can go wrong. Simulator, tons and hours of simulator work. So a lot of the maneuvers which we wanted to do, for example, but we could do them only if the aircraft was fully serviceable. You couldn't guarantee that you can tolerate a single failure. So then you obviously have to drop those kind of maneuvers. Some maneuvers where there is a strong potential of exceeding your envelope, you need to set aside, because again, it becomes a skill dependent activity. So this is how the whole thing came together, and it was actually many months of work directly on this profile. But like I've described to you, it was many years of thinking about displays, starting from even I was the designated display pilot of the Sea Harrier. Even there, for example, I learned that the Sea Harrier displays, because they are V-stall, largely dependent on V-stall, which means wind dependent. You couldn't ignore the wind. So, for example, the Sea Harrier display had to be mix and match. You could not have a fixed, rigid display routine of a sequence. In the sense, like if today the winds are down the runway and tomorrow the winds are completely crossed up by 90 degrees, you cannot insist on doing exactly the same maneuver, because you will get into deep trouble. So there are enough times when either you need to choose a different maneuver or sequence the maneuver differently, do it in the opposite direction, or some such thing, which is complete anathema to the way militaries control display flying. It's a very, very tightly, very heavily, extensively documented profile. It's literally like a series of hoops that you need to go through. It's a proper gymnastic routine, which is
there's a whole committee that approves
and it goes up many levels of the command chain. Any deviation from it is you're going to get in the neck. But the moment they designated me Harrier display pilot, I had to first convince them that you will drive me into the ground if you do it that way. You have to give me this flexibility. I will list out the maneuvers and list out the conditions, and on that day I will have to do a la carte pick and mix and match. So whereas here, so for example in Bahrain, we had to cope with a scenario where unlike most display venues, the crowd was at one end of the runway, not in the middle of the runway. So naturally the thing was, what do you do after you take off? Normally you try and show as short to take off, as quickly as possible, get off the ground. But if you did that, you would be so far away from the crowd that it didn't make sense. The other option was to line up halfway down the runway, and where those old adages come out, runway behind, sky above, fuel left in the Bowser, of no use to man or beast. So it would be foolish to get into trouble where having lined up with 5,000 feet of runway behind you. So you say, okay, then in that case, we'll get airborne and stay low and do a high energy maneuver at in front of the crowd. So that's how that business of staying low and then doing a maneuver came in, rather than as short as possible a takeoff. Now you can't take that and do that in a different venue where the crowd, let's say, is at the center of the runway, because you're starting from one end, you're taking off, and then going to the other end, far away and out of sight, doing some maneuver. Doesn't make sense. You have to adapt the routine to each one of these locations. So with all of this, you will have seen that the people who need to display the aircraft have to be the OEM's test pilots, because they're the only guys who can create this and do this flexibly enough and still show you, they have the resources to throw at scientifically creating a safe and interesting and a display that puts across the message. I am a firm believer that OEMs should display aircraft, and not certainly when it comes to where you're trying to show your aeronautic prowess or you're trying to sell a product. It should not be service pilots, because service pilots are not equipped, and they're not trained to think in this manner.
Right. So, sir, you've flown also with some of these visiting air chiefs and things like that. And what are those routines like? What is the purpose of some of those sorties?
See, those are, again, you need to do a little bit of homework as to what is the kind of person coming to you. Is he already a fighter pilot? What kind of aircraft has he flown? What is the idea with which he's coming to see you? What are you trying to impress him? So when you fly a USAF chief, or you fly a Sri Lankan Air Force chief, or a Turkmenistan Air Force chief, you can't approach it the same way, because you might be hoping to sell it to one of the countries. You're another country, you're just trying to impress them about how far you've gone down your development. I mean, they are different. There are completely different messages for different kinds of people. So again, if he's a non-pilot, for example, you naturally have to keep it to a low. The kinematics have to be calm. You can't have a very, very dynamic display and have him getting airsick. At the same time, if you know that he's a out and out true blue fighter pilot, you are going to have to give him controls. You cannot stick him in the back seat and say, "I'll show you." So there is a fair bit of planning that needs to go into how do you target a particular person of interest whom you want to put a message across to. Whether is it a press reporter, is it an aerial photographer, is it an air chief, is it a minister? What is the message that you're trying to put across? Now, some of the things that we have kind of figured out is some of the strengths of the aircraft we must try and show. Certainly when you're trying to, you're looking at somebody who could, if not right now, then in future be a potential customer. Then what you cannot show from outside in an air display, obviously the real maneuver capability of the aircraft you can only show in a display format, because even if you give him controls in the air, first of all, it's a two-seater, not the single-seater. So two-seater performance is not the same as the single-seater performance. The second is you can't let him do the same maneuvers that you can let a display pilot do in front of him. So then you have to look at these sorties as an adjunct to that thing. That is, what is it that I cannot show in the display? So for example, I can't show you how well my displays have been designed, my multifunction display formats have been designed. How well have the sensors been put together? Can I work with 3 sensors at a time, and therefore handle targets which are deeply camouflaged? Things like that. Those are the kind of things that you put together. So very often you might even choose to weigh down the aircraft with drop tanks, with an LDP, with maybe even a practice weapon for that matter. You would actually deliberately load it up, and that means you're sacrificing performance in the with the purpose of showing him specific capabilities. So you'll see that each one of these things actually, when it comes to, when are we going to sell an aircraft to another country, it's really going to be when we learn this full spectrum and we internalize this full spectrum of activities that need to be done, including our publicity material.
Right.
For example, now this is a slightly politically incorrect thing to say, but it just shows you that you have to think from a different perspective. Now, since we have been struggling so hard to convince our own country that it is worth spending this much of time and effort on making these platforms, and you're always fighting criticism of the programs, etc. and all. So if you see, a lot of our publicity material has a multiplicity of agencies. I mean, it takes great pride in showcasing the number of agencies who have contributed towards making this platform. Whereas if you see Boeing or Dassault, you don't get to know what their who their sub vendors are, right? You don't get to know, or who are the agencies that contributed to them. So what is the difference? Now, for a real customer, if you're showing an audience and you're just trying to fight criticism of the program, this kind of publicity material is great, with a whole lot of mugshots of a whole lot of agencies. But if you are talking to a serious customer, now he's going to get frightened by the fact that whom do I deal with? Because a customer typically wants a single point of contact and a single point of responsibility. He doesn't want to be bounced around between all your various downstream agencies. So this thing is, I think, the next big area in which we need to apply, put some really talented individuals, get a concept going, which runs across, year by year, not just a airshow by airshow kind of everybody reinventing the wheel or just doing the same thing, repeating the same thing going forward. These are all things that we're going to have to do if we truly hope to sell aircraft. And it's only when we truly hope to sell aircraft will we have the money to actually invest in really high-end aeroplanes.
Roger, report type Southeast, connection for Midwest and field selected.
Well, folks, that's all we have time for today. However, my conversation with Commodore Maolankar carried on. We did almost 2 hours and 45 minutes in total. So stay tuned next week for the second half of this conversation. In the meantime, sign up for updates at blueskiespodcast.com. There you'll find links to follow us on Twitter, Facebook, and Instagram. You can also write to us with your comments, questions, suggestions, and feedback from the website or to blueskies@prganapati.com. Subscribe to the podcast on any podcasting platform such as Stitcher, Google Podcasts, Spotify, Apple Podcasts, and even on YouTube. If you like what you heard, share it with your friends, give us a rating in your favorite podcasting app, and write us a review. It will help other people find us. I want to give my thanks to Saurav Chordia for our logo and Prithvik for the music. I want to reiterate that all the views expressed here are personal, and this podcast has not been approved by or reviewed by the Air Force, Ministry of Defense, or any branch of the government. In the meantime, stay safe and Jai Hind.